Hello guys, today we will finish the topic of dielectrics. So we were discussing, we were discussing materials in the electric field. Right, so we started the discussion about dielectrics, and we're gonna finish it in this lecture. We're gonna focus on doing analysis. Okay, so. Right. So we talked a bit last time, or we explained a bit last time about polarization. What does polarization mean? Essentially, it means imagining or having a mental image that in any medium where the electric field exists, and in general electromagnetic fields, electric or magnetic fields exist, those mediums have certain properties embedded in them. They're not just empty, right? They have what's called bound dipole moment densities, or what we also call polarization, right? So when an electric field exists in the medium, in the material, whether that material is bona fide material or just empty space, which as far as the theory is concerned is also considered a kind of material, right? Something happens within the medium, right? Some things wiggle and move within the medium, and those things are the dipoles. So there are like dipole moments represented by arrows in the material, and there are like an infinite amount of them. It's like a distribution of dipoles, and the polarization vector is a quantification of the dipole moment density. Right? So if you take the polarization vector and multiply it by a volume element, I use prime to indicate that it's like a source, right? You get a dipole moment. In the same manner where if I take a charge density and I multiply it by a volume element, I get a charge. So I take a charge density, multiply it by a volume element, I get a charge, volume charge density of course. I take a polarization vector, multiply it by a volume element, I get a dipole moment. This is something like a positive charge and a negative charge that are very close to each other. Some people draw it like this. Okay, so the idea is that within the material, the electric field will cause those small dipole moments that are distributed everywhere, which are bound charges. Those are bound charges. They cannot move. They are like tied to the fabric of the medium. They cannot move, but the only thing they can do, well, they cannot move from point to point, but what they can do is they can reorient themselves and then stretch or compress in reaction to the electric field acting on them, right? And this is the pretty like basic picture in electromagnetics, classical electromagnetics, viewing the medium as something where those dipoles exist, right? Now, when we study dielectric materials, actual materials like some compound or something, those will have actual literal dipoles, right? Why? Because the material is going to have a bunch of protons and electrons that are bound to the protons, so they cannot move, right? And then when the electric field acts on them on the crystalline structure or atomic structure of the material, those charges cannot move within the solid material, but they can stretch and compress and orient themselves, right? So within any real life material, there is like a literal polarization that's occurring, right? So that part, that's the part that we're going to study in this lecture, and that's essentially will be the characteristic of dielectric materials. Dielectric materials are materials that have bound charges in them that cannot move, right? But that can stretch and reorient themselves in reaction to an electric field acting on the material, right? But beyond that, even empty space itself, even in empty space with no material, the theory itself imagines those dipoles exist in empty space too, right? They could be of different strength than some. It could be weaker than some material or stronger some other materials, but they do exist in empty space. We suppose that they exist in empty space. That's part of the model. That's part of the right model of empty space that EM theory includes. Right. Now that doesn't mean that there are literally dipoles in empty space. Again, I mean, EM is not the final theory about what empty space is. EM is only an approximate theory. I mean, later we found out that there are more accurate theories to describe empty space, right? Like quantum field theories or quantum mechanics. More modern theories describe empty space more accurately, right? But EM theory, electromagnetic theory, is still valid in its domain of application, right? In its domain of application, which is emission and absorption of radiation, radio waves, electrical circuits, different electromagnetic properties of materials. So in its macro domain of application in our world, it has its applications, but it's not the final story about what really constitutes empty space. You know, in the same way that Newtonian mechanics, although we know it's not 100% valid in terms of modern physics, right? In terms of the modern understanding of the world, it's still very useful for its domain of applications. So, for example, when we send a rocket to Mars, we don't worry about general relativity or any of Einstein's theories about gravity. We just use the Newtonian model of gravity because it's good enough, right? For that application, right? So when I'm saying, I mean, the point that I want you to take from this is that when I'm saying, hey, empty space has dipoles in it everywhere, I don't mean that literally. I mean that as being part of the model presented by the theory. That is still useful and predictive in many ways, although it's not the final story. Okay. When it comes to materials, of course, dipoles do exist, literally. Okay. So, all right. So we want to, how can we use the polarization? So we have material, right, or empty space, and we have the electric field, and it causes polarization. How we can tie this polarization to what we know about electrostatics? Because up to this point, what we know about electrostatics is this. We know the axioms, right? We know that divergence of E equals rho over epsilon naught, right? Volume charge density over epsilon naught. And we know that curl of E is 0, right? So that's what we know, right? So the only way to tie polarization to those fundamental axioms that we stated is to somehow tie polarization to charge density, right? Charge density would be the evidence of polarization, right? I'm claiming here in space or in material, I apply an electric field and polarization occurs. What's the evidence that there is polarization? Well, one way to detect evidence of polarization is to see, did any charge density occur in space due to this polarization, right? Sometimes it will, sometimes it will not, right? So for example, if I have some material, and this is the grid that I drew to approximate the dipoles, right? So D approaches 0, right? And every point in space, there's a, let me draw it again, there's a dipole, right? So the idea when the electric field is applied, all the dipoles will rearrange themselves, right? So that they're in the direction of the electric field, right? Now the thing is, if all the dipoles arrange uniformly, meaning if I look at every point and like say I have a dipole that's stretched and then next to it, the dipole that's in front of it is stretched by the same amount, and then the dipole next to it is stretched by the same amount, right? What will happen is that, you know, in a small region of space, I'll have more positive charge, but I'll also have more negative charge. So the stretching of the positive charge will cancel the stretching of the negative charge. And generally, if the stretching and compression is uniform, I won't see any charges as evidence of this polarization. The charge distribution in space will still be 0, right? But if I have uneven polarization, meaning I have some dipole that's stretched a lot and then next to it a dipole that's only stretched a little, I'll have more positive charge than negative charge, and I'll have a net positive charge at every point in space, right? So the statement that I can make, which is non-rigorous at this point, is that, hey, if I have non-uniform polarization, meaning a polarization vector that varies between points in space, I will see evidence of a charge density. Once I see evidence of the charge density, I can use the first axiom to tie this extra distribution, charge distribution, to the electric field. That is the doorway, so to speak, to tie this polarization to what we already know about electrostatic, which is the two fundamental axioms. Okay, and that's why I talked about the voltage that arises through due to a dipole. Remember, I talked that if I have a dipole, the voltage that and the voltage at a point, Vp, is going to be, so I take this distance r and then this vector r hat towards the point, and then the potential is going to be just p dot r hat over 4 pi epsilon naught r squared. We derived this last time, right? So that's the reason. The reason we derive this is because we need this now because we want to find what the distribution density is that arises from a certain dipole distribution. So we want to first find the voltage and then use the voltage to predict what the charge distribution needs to be to give us that voltage. That will be our route, right? So let me set this up. Okay, so we have the material. This is some material, some medium. It could have a boundary, that's fine. And then we have a certain polarization vector in the boundary. For whatever reason, I mean, it could be an external electric field, it could be some initial configuration. I don't know how we got there, but we got there. And then we have the dipoles with different strength and then different orientations all around in the material. Right. The question is, right? So those are dipole densities, of course. And, there's an infinite amount of dipoles in there, right? If I take a small volume of this material, dv prime, the dipole moment of this small volume is going to be p dv prime, right? Now the question is, at a certain point inside this material, what would be the voltage at that point? So let me draw an arrow. So this is a distance r. This is r hat. the unit vector towards this point in space, right? So we got that result, right? So it's because this is a differential dipole moment, right? It will give me a differential voltage at that point. To find the total voltage, I have, of course, to integrate over the medium, right? I have to integrate over the whole medium. I'm using superposition. Every small box in the medium is gonna contribute to the voltage at P. But the differential value of the voltage at P is gonna be P dot R hat over 4 pi epsilon naught R squared dV prime. Okay, so what's the complete voltage at that point? Well, we have to integrate over the volume. This is the volume, by the way, V prime, the whole volume, right? So let me call it V, just V, okay? And so it's the volume integral V prime P dot R hat over 4 pi epsilon naught R squared dV prime in volts. Okay. Now here is oops, right? So here is what we want to do. So we calculated the voltage, right, at that point. But the idea is that we want to find the charge density. So we have to kind of ask ourselves, hey, what this polarization should be equivalent to some charge density. What charge density in the material or in the medium is going to give us the same voltage? Right. So remember what we said, if we have volume, this is an early result that we got. If we have a volume charge density, the voltage we know at the point is going to be 1 over 4 pi epsilon naught over the volume rho v over r dv prime. Remember this result? So I'll highlight this. This is an early result that we got, right? This is the potential due to a point charge, right, or a differential element. You just take rho v times dv, that gives you the charge, divided by r, that gives you the potential. The potential is always proportional to the inverse of the distance, not the inverse squared, unlike the intensity, electric field intensity. So this, if I compare this integral number 1 with integral number 2, they have to be equal, right? Because the voltage is the same. The only way they can be equal is if the volume charge density, and let me call it the volume charge density due to the polarization, not any free volume charge density, just the volume charge density that appears, that is evident in the material due to the polarization vector, right? So that I just need to take 4 pi epsilon out, right? And then I take 1 r out. It's evident that the charge density is going to be P dot r hat over r. Right? So this suggests that this is how we tie polarization to charge density. Okay, so this is still like not very useful because, okay, how do I tie this to the fundamental axiom, the first axiom here, axiom 1? Then this is axiom 2. It's not clear how can I tie it there. I mean, I can plug it in there, but I won't get anything useful. That's one problem. Another problem is that this doesn't tell me what happens on the boundary, right? So if I have a material and I have polarizations in the material, plus minus, plus minus, plus minus, I might have some volume charge density, but at the edge of the material, if I have an external field, I'll have only one part of the dipole hitting the edge, right? Either the negative or the positive. So I expect to see at the boundary, a surface, let's call it rho ps, a surface charge density, right? So this formula doesn't account, this comparison does not account for the surface charge density. I mean, the material could have a boundary, right? So we want to express this voltage, a better way to express this voltage is in terms of the volume charge density and the boundary and the surface charge density. We want to get a form that's more useful for us than this form. This is still correct, but this doesn't help us much when we plug it into the fundamental axiom, right? There is another form that is useful that we can derive, and I'll show you how to derive it now. Okay, so I want you to notice something. Notice here we have this term. We have r hat over r squared, right? So imagine this. Shall I do it, or I'll redraw it? Okay. So this is the material. This is the volume charge density. This is the dipole p dv hat. And then we said, hey, the point we're interested in is a distance r, right? And the vector is this way, r hat. Okay. Typically, if I have an origin, if I have a point like an origin, and I have a scalar field that's 1 over r, right? The divergence, what's the divergence of u? What's the or I can write it, what's the divergence of 1 over r, right? The divergence, not the divergence, sorry, the gradient of 1 over r. What's the gradient of 1 over r? Well, if you recall, gradient for a scalar field in spherical coordinates is this, du over dr r hat plus 1 over r du over d theta plus 1 over r sine theta du over d phi, right? Now I'm interested in the gradient of 1 over r, right? But that tells me that here the scalar field is 1 over r, right? So it's not a function of theta or phi. So those terms will be 0. So I only need to take differentiated with respect to r. What's this? This is going to be minus 1 over r squared, right? 1 over r, when you differentiate it, you get minus 1 over r squared, and then r hat. Notice this term, r hat over r squared, shows up here. So there is a divergence, there is a gradient of 1 over r here, right? We have to figure out then how to plug it in, right? So the crucial point here, this is a tricky point. Pay attention, please. So the crucial point here is that if I take P to be the origin, right? And if I take P to be the origin, I can find the gradient of 1 over r to be this, right? But this presupposes that the r hat vector is in this direction, right? If you have spherical coordinates, the r hat vector will always be in this direction, right? Moving away from the origin, typically, at every point in spherical coordinates. But the way we build this problem, we are integrating over the material, and the r hat vector is pointing from every point in the material to P. It seems that in this problem, the r hat is always, so this is P, let's say. R hat is always, instead of pointing in that direction, R hat is always pointing in the opposite direction. So for this problem, the gradient actually, R hat, instead of R hat, we should have minus R hat, right? Because R hat is pointing in the opposite direction that we're interested in the integral. So this should be minus R hat, and we should have a positive here, right? This is kind of like a subtle point. I want you to kind of, it's a subtle point. I need to kind of like go through, convince yourself that this is true, right? Typically, when you, the key is that whenever you calculate the gradient for a scalar field in spherical coordinates, r hat is always pointing away from the origin, from the point, right? But then the way this problem is framed, R hat, because we're finding the voltage at point P, R hat is always pointing towards the point. So the R hat and the gradient should be the negative of the original R hat. That's why we get a plus instead of a minus. The reason I'm saying that is because now I want to rewrite this, but instead of this, I'm going to put gradient 1 over R instead of what you would expect to put minus gradient 1 over R. But no, that's not correct. You need to put gradient 1 over R. So let's rewrite this and put the gradient. So that tells me that I can rewrite the voltage at point P as follows. I can say 1 over 4 pi epsilon naught. I took the 4 pi epsilon naught out. I integrate over the volume. And then R hat over R squared, I said I can write it as gradient 1 over R, right? P dot gradient 1 over R dV prime. Okay. So this is the new form of the voltage now. What we do next, the next step is applying the Leibniz rule. The Leibniz rule is just like it is the product rule for differentiation. Remember when we were talking about vector calculus and we said the gradient, the divergence, and the curl are just, different forms of differentiation, different forms, different generalizations of differentiation in higher dimensions, right? So they should all have a version of the product rule, right? That's one of the basic properties of differentiation. The product rule applies. So the version of the product rule that we want to use is the one for divergence. So if I have a divergence of a scalar field and a vector field, so this is a scalar field, right? And this is a vector field. The Leibniz rule states that I can use the product rule, like, I can do the scalar field times the divergence of the vector field. I took the scalar field out, plus the divergence of the scalar field dot the vector field. Okay, I can rearrange this so that I get well, what is this here? This term here. This term here is a vector field times a gradient, right? So this matches this term, right? So I can rearrange this equation so that I get this: the gradient of the scalar field dot A equals the divergence of the scalar field times vector field minus scalar field divergence of A, right? I can apply this there, so I can rewrite now, right? So let me put in the P and the 1 over the divergence 1 over R. So this is like P dot divergence 1 over R, right? So in this case, P is A and 1 over R is phi, right? That's the connection you have to make in your mind, right? And dot product, it doesn't matter what do you do first. I mean, it's commutative, right? So this equals divergence of 1 over R, so phi is 1 over R, P, the scalar field multiplied by the vector field, minus 1 over R divergence P. Now we take this thing and we substitute it into the integral. And that's the next step. So when we do that, we get Vp equals 1 over 4 pi epsilon naught volume integral 1 over Rp, right? Plus, I want to take the minus inside the integral for reasons I'll show soon. V 1 over R divergence P dV. Okay. Now this part, I can change this volume integral into a surface integral through integration by parts, not part. Sorry, no, through the divergence theorem, right? Right. This is a divergence inside a volume integral. We said we can through the divergence theorem, we can the theorem we can evaluate this as a surface integral on the boundary. Right, so this will give me Vp equals 1 over 4 pi epsilon naught surface integral on the boundary. So the material has a volume V, the boundary is surface S, right? So I integrate over the boundary, it's a closed boundary, right? And then I could say P dot ds, but I want to write it in a more suggestive form. I could say I want to write it as P dot n hat, where n hat is the normal vector on the boundary. It's the vector that's 90 degrees everywhere on the surface. That's what n hat is. So P dot n hat over R right ds hat. So I just took this thing here and took the surface integral of it. That's the divergence theorem, right? ds prime is the surface element on the boundary. Okay, plus the same volume integral. Oh, this is minus, of course. This is minus. Okay, so volume integral minus divergence P over R dv prime, dv prime. Okay, so what does this look like? This part looks like a voltage that arises due to a surface charge density. Why? Because we have this term here that's a coulomb over meter squared, right? That's what the units of P are times the surface, right? So this looks like a surface charge density. Right, and we know what the voltage is due to a surface charge density. It's the surface. So you take the surface charge density multiplied by a surface element, right, and then divided by R, and then you integrate over the surface. We did that before. So this looks like a voltage that arises from a surface charge density due to polarization. This looks like a voltage that arises due to a volume charge density, right? It has the same form, So remember we had the surface integral of rho s over r ds prime. We did that in the past, and this is the volume integral of rho v over r dv prime, right? So the surface charge density is this term, which is P dot n hat, right? And n hat is the normal vector at the boundary of the medium, right? And the volume charge density in the medium is going to be this term, right? It's that density divided by R. Integrate over the volume gives me the voltage, right? So I'm kind of like using the formula that I already know, right? So that tells me the volume charge density should be minus the divergence of the polarization. And this is it. This is the link between the state of the polarization vector in a medium and the charge density and surface density that appear on the medium. So this is the link between the polarization vector inside the medium, whatever the cause of the polarization is, whether it's spontaneous or arising due to an electric field, whatever it is, there's always a link between the polarization vector and the volume charge density due to polarization that appears in the medium, and surface charge density on the boundary due to polarization. There might be other charge densities in the medium. There might be some free charge densities, you know. We don't care about those. We only care about those that arise due to the state of the polarization. So those charge densities that arise due to the state of the polarization will always have this form. This is the link, this is the relationship between P and rho. Okay. Now we have the link that allows us to go back to the first axiom and see how the polarization affects the electric field, right? So in the first axiom, when I say rho here, I mean any charge, whether it's free or bound, total charge, essentially, total. So I can rewrite this as divergence of E, rho volume, this is the free charges, plus rho PV, the charge densities that appear due to polarization, right? This is polarization. Right? And this could exist in free space, or it could exist in the material, right? Over epsilon naught, of course. So I can do some manipulation, move epsilon naught to the other side, right? Epsilon naught E. Right, and then I can move, this gives me rho V plus rho PV. Remember when we said that in free space, this is D, right? This is D in free space, right? Right, only in free space, but this is not D in any general material, right? Because we haven't found D in a general material yet, right? This is, I'll erase this actually. So at this point, this is just epsilon naught E, which is D, the flux density in free space. In a different material that's on top of free space, the flux density will be different, and we'll see why. Right? So now I can rearrange this and move rho PV to the other side, minus rho PV equals rho V, the free charges, right? And I know that rho PV is minus, I found this result, is minus divergence of P, polarization vector, right? And this is the polarization of the material. Okay. This is, by the way, the polarization of empty space. This is how you look at it. And this is the polarization of material on top of empty space. Right? So let me plug that in. What do I get? I get divergence of epsilon naught E, minus minus becomes plus, plus divergence of P equals rho V, right? And we know that divergence is linear. So if I have divergence of A plus B, two vectors, the result is divergence of A plus divergence of B. Divergence has a basic linearity property. So I can use this property to rewrite this as divergence of epsilon naught E plus P, right? This factors into those up here, equals rho V. Now this whole thing in here is the D vector, the flux density, when there's a material with a certain polarization that exists on top of free space. Right? So this is the D vector for a general material, general dielectric material. So this is the main result now. The flux density, which is the total polarization, we can look at the flux density as the total polarization equals the polarization due to empty space, this term, plus the polarization vector due to the material. This is the whole story of D. Okay, so P represents polarization in excess of the polarization that already is assumed to exist in free space, right? And P exists due to the dipoles that exist in the material. So the material has atoms and nucleus with protons and electrons, and those are fixed in space, tied together. They cannot move, but they can stretch and compress and reorient themselves depending on an external electric field. Okay, so we could end the story here and just, for different materials, we can say that, there's certain P, but I mean, that's still not very intuitive and hard to utilize, because the story doesn't end there, because P really is a function of E, right? I mean, intuitively, I mean, if you have a stronger electric field intensity, you have more polarization. The question is, how is P a function of E in the material, right? And then one of the simplest relationships we can think of is just a linear proportional relationship. So P is simply linearly proportional to E, and it's just a constant. Take E times it multiplied by a constant and you get P. So typically this is defined to be, the relationship between P and E is defined to look like this. P for any material is defined to be relative to empty space to look like this. So epsilon naught ZE E. This is called the electric susceptibility, right? Right. So this is the linear relationship between E and P. If E doubles, P doubles, but by how much? By a factor depending on epsilon naught times the susceptibility. Right? We divide it this way because we wanna quantify materials compared to empty space. Right? If a material has Z of 1, that means its polarization is equal to the polarization of empty space. If its Z is 2, susceptibility is 2, that means it polarizes double. Right? Oh, by the way, what happens if a material is in empty space and it has Z that's 2? What's the total polarization? It will be 3 times, right? Because you'll have empty space plus 2 empty space polarizations, we'll get 3. Okay, so we can take this. So this is a simple enough formula for polarization. We can take it and plug it back in here, and we end up with this formula: D equals epsilon naught E plus epsilon naught susceptibility times E. We can now take E out, and take epsilon naught out. I end up with epsilon naught 1 plus susceptibility E. And this is the most common way to quantify the properties of the dielectric materials. You can use the susceptibility, right? Right, so that's one way. Or you can lump 1 plus Z as what's called epsilon R. Right, so I can say, instead of epsilon 1 plus Z, I could say epsilon naught epsilon R E, where epsilon R is the relative permittivity, right? Or I can combine this whole thing and this whole thing to get D equals epsilon E. Epsilon is called the permittivity. Also, it's called the permittivity, but because there's no small o here, it's the permittivity of the material rather than the permittivity of empty space. Right? So it's a bunch of different constants, but it's clear what they all mean. I mean, the relationship between them, right? So we write D equals epsilon E, where epsilon, in summary, is just epsilon naught epsilon R, epsilon naught is the permittivity of free space. Epsilon r is a dimensionless quantity. That's called the relative permittivity. Epsilon is the permittivity of the material. And then we can also factor this out more, and we say that epsilon r equals 1 plus the susceptibility. Right? So, I mean, it's simple. I mean, it's just different constants. It might seem confusing why the different constants. That's the historical development of this material, of this study, but you should know how they relate to each other, and right. The most common constant that you would see in tables about materials is the relative permittivity. Right? Rarely would you see the susceptibility. Of course, epsilon r is dimensionless. Right? And of course, z is also dimensionless. Okay, so this is the big picture. This is the essence of how you find. Right. So if you have an electric field, the idea is that in an empty space, you have the field, right? The field causes polarization in empty space, and you get the flux density being epsilon E. Again, remember we said the flux density is the measure of the polarization in empty space. What if you have a material and this field passes through this dielectric material? You'll get a different D. This D now inside this material will not be epsilon naught E, it will be epsilon E. Right? The material will have a different epsilon, but this epsilon of the material that determine the total polarization in that material, which is the polarization of the material plus empty space, is going to be a compound of it will be one epsilon naught epsilon r, which is epsilon naught 1 plus z e, right, which is epsilon plus epsilon naught z, which will be like, you know, the polarization of empty space plus some excess polarization due to the material. This is all multiplied by E, right? That is described here in terms of how it relates to empty space, right? Z of 1 is a material that has a similar polarization to empty space, right? Z of 2, Z of 3 has 2 times, 3 times the polarization of empty space. Okay, so this covers it at this point. There are some other small things we need to describe, but yeah, this is it for now. This is oh, by the way, epsilon naught is the permittivity for empty space, but it's not the permittivity for air. So the permittivity for air is something else, right? But I don't remember the exact value. But it's something that's kind of like not much bigger than air. So it's something like that. I think 1.006. I'll double check later, but that tells me that oh, epsilon r, the relative permittivity. That tells me that it's close to air, right? So what is this? This is, we said this is 1 plus ZE. That tells me that the susceptibility is 0.006. That means the polarization of the gas molecules in the air is 6,000ths that of the theorized polarization of empty space. So that's why we could consider air to be approximately empty space. Right. So next time we will talk about the relative permittivity of different materials. We will talk about dielectric strength, we will talk about linear materials, homogeneous materials, isotropy, what those terms mean, and then hopefully we can start talking about, I think the next topic is capacitance perhaps. So we'll start talking about capacitance and what does it mean by capacitance. We have to kind of understand what does the farad mean in epsilon naught. So we said epsilon naught is farad per meter. What's the significance of this farad? Alright guys, thank you for listening, and we'll continue next time. Good night.